Okay, hello everybody, and welcome to another GBO Science Lunch. Thank you all for coming in this week after extenuating circumstances last week. So today we have our guest speaker, Luis Henry Quiroga-Nuñez, who will be talking about his work characterizing galactic stellar populations. Now, during his talk, if you have a question, feel free to unmute yourself and ask him. Otherwise, I think take it away, Luis.
Okay, thank you, Jesse. And also I want to give thanks to Natalie, who also invited me to give this talk. I'm going to talk to you about characterizing some stellar populations, but particularly I want to give some emphasis on the synergies that we can get from different observations, different frequencies, radio, infrared, and optical surveys. This is, of course, not my work only. I have been collaborating with different radio campaigns, as you will see it, and also other spacecraft surveys that has contributed dramatically to my science, to my research. If you have any questions, please feel free to stop me. I will move between topics, so I like the interaction. So please feel free to stop and say, I want to ask a specific question about that, okay? I will not following up much of the chat, but probably, again, you can just go for it. So let's start. So this topic is this talk, I want to highlight two particular projects. One is the Bessel project and one is the BAADE project. Probably you have heard of those, something. If not, I will do a quick recap. But more importantly, I want to add or include in this talk what we can get, again, from other surveys in other frequencies that can add to these radio campaigns. So both of these projects, Bessel and BAADE, they work for masers, but they work in different galactic populations, stellar populations. Bessel works more with high mass star forming regions. BAADE works more with the bold stars. So they are completely different populations, and we will see how other astrometric measurements in other frequencies can have. So let's start with the Bessel survey. So the Bessel, it stands for the Bar and Spiral Structure Legacy Survey. It was a BLBI key science project led by Mark Reed in the CFA, and the aim of this project was to study the Milky Way spiral structure and the kinematics of these arms in the Milky Way. And for that, they have used water masers coming from water and methanol masers coming at 22 gigahertz and 6.7 and 12 gigahertz. And they have used particularly the BLBA to study this. So they have follow-ups of around 400 high mass star forming regions looking for emissions at these frequencies. And with that, they were able to find 6D information, so phase space information. The accuracy that they were able to reach was close to 10 microarc seconds. In some levels, we were able to reach, and to surpass that at 8 microarc seconds, I think that is the best measurement of a parallax resolution that we were able to reach. And we were pushing the sub-microarc second resolution, but we were not able to build it so far. And for this, we have used 5,000 hours of BLBI observations, particularly with the BLBA, which is a lot, of course. In 2014, the first publication came out trying to trace, and you can see there, where are these high mass star forming regions after following up. I think that this publication was for 100 of them. But of course, more publications are coming. There is a new one of 2019 with, I think, that 230 or so sources. And the idea behind this, again, is try to find where are these spiral arms, because there are fundamental questions here that we don't know, like how many arms are, or if they reconnect to the other part, are there some kinks in the arms, how this works. So they were able to produce, again, some nice rotation curve, and also characterize or estimate the fundamental galactic parameters of the galaxy, which are essential if you want to calibrate some sources in the galaxy, as giant molecular clouds, for example, or even extragalactic measurements needs to be calibrated by these sources, but these parameters, sorry. And in one of the publications in 2017, the Bessel Survey even was able to publish one source in the other side of the galaxy. So you can see here, this cyan star, which is down. Um, this is a maser that was detected again in the other side of the Milky Way. So this kind is the research that you can do with this, and it's very impressive because it's giving again some hints for future observations or to calibrate particularly astrometry at other at extragalactic studies. But I was within the project, I came interested in one particular source, which was S269. And S269, you will see why it came interesting for me. But for now, it's just a high mass star forming region that is in the anti-galactic center, so pointing to the other side of the galactic center, and was observed by BETA for the first time in 2004 in order to achieve a good distance estimate to this source. So you can see in the left, the high mass star forming region in optical regime, and in right, where it's coming from 2-mass infrared regime. And the central cross is showing you more or less where the maser emission comes. In 2004, again, this was the text. This was follow up for the first time, and they found a particularly elongate maser emission that you are seeing in the right part of your screens. This elongation was weird because you usually don't expect that for for maser emission, but they report that, and they were able to trace they were able to trace the proper motion and the parallax for this star, finding a distance of 5.28, that's the value there, kiloparsecs. And again, this is in the anti-galactic center direction. So, but what happened after is that in in 2014, Asaki, another publication in APJ, reanalyzed the same data. It was exactly the same data, but they didn't use this elongate maser, but they tried to use other masers in the data in order to track the the proper motion and the parallax of this source, and therefore the distance estimate. And they have found again that this is not at 5.3 that Honma was claiming, but 4 kiloparsecs away. So there was this discrepancy depending of the shape of the maser that you use. But more importantly, this source is particularly interesting because it's one of the sources that are really far away from the galactic center. It's more or less a 13 kiloparsecs, and is a good test of how flat the galactic curve is for at this long galactic radius. So this came interesting for Bessel, and in 2014 that there was this publication. Let me see if I can do a zoom. This is one of the red sources that you see in the top, the one in the top. So this source was also used and fundamental to characterize how is the shape of the outer arm there. So in Bessel, there was a decision that we should observe once more again because there is a discrepancy of the distance, and this one particular is special. So we observed this source again in 2015 and 16 using the BLBA. And this is the publication that came out in which we were able to find a lot of masers, and with a lot of masers, we were able to trace pretty well the distance to this source, finding that is around 4.15. So Asaki seems to be right in that way. But something that came also pretty interesting, and before I do that, so again, when we move that star close by, and these are the arms are in black, and the colors in purple and red are showing you that it seems that the outer arm breaks, or there is a kink, we want to say that, at more or less a galactic latitude of 140 degrees. So again, these kinks are not unusual. They happen. We have seen it in extragalactic sources, but this one was again particularly interesting for characterizing the arms within our galaxy. This one was one of the results of only moving that star, and Also, something interesting that we have found, let me see if I can pass this, yes, is that we were able to find again the same elongated source with the BLBA. Just as a reminder, in 2004, when it was observed by Hodma, was beta observations with the Japanese array. Here one was with BLBA 12 years after, and the elongated source is still there. And that was particularly interesting because masers do not live that much. And we were actually able in that publication to trace back how it's changing or the offset of the source with respect to the two observations, one in beta in 2004 and one in the BLBA in 2016, and match that indeed we are finding a good parallax and proper motions of this source and confirm the distance to this source. But again, something interesting about Bessel is that Bessel is producing a lot of sources. A lot of let me see if I can pass. Oh, sorry, Bessel is producing a lot of sources, mostly in the North Galactic region, because the BLBA, the European BLBA network, the Beta array, they are in the north part of the galaxy of the Earth, and therefore are pointing to quadrant 1 and quadrant 4, basically. But with that, we can indeed try to recover the fundamental parameters. But something that came to our mind is what happened if we add more sources. I mean, if we simulate that we have more sources, and or what happened if we add more sources from the southern hemisphere. And that was a work published in 2017 in which we actually try to test how new southern observatories coming as the Square Kilometre Array or the African BLBI network could contribute with sources. And something surprising is that even that they can add more sources, they won't be able to do much even with high sensitivity, because in order to refine the galactic parameters of the galaxy, which was the scientific goal of this, you have to add much more sources, but a lot more. So, and here I want to say that here is when other wavelengths come in, and I want to show you this for particularly the source of S269. Sorry, I have to move here again. So in S269, one of the questions was, okay, we were able to trace the source, but what about Gaia, for example, is producing billions of sources, and how many sources seems to be part of the same stellar association? So again, we are not trying to find the optical counterpart that is producing the maser, because of course we cannot see that in optical regimes, but and this is a publication again in 2018, we were able to show that indeed Gaia can find sources that already dissipate the gas and are part of the same stellar association. So in the left, again, you are seeing now the optical, in the right, the infrared, and the red sources are showing you those sources that Gaia seems to be more or less in that region, but also within the distance expected for this star. And in the right, that is the infrared one, you are seeing how these sources move with respect to the maser, that is the blue small arrow there. So there are at least 3 sources you can see that close by to the blue arrow, that those are the 3 red arrows that are moving similar, they have a similar distance estimate from Gaia. And when we try to put it in a Hertzsprung-Russell diagram, or sorry, this is absolute magnitude as function of color, you were able to see where are these stars without the blue, the yellow points in the blue region. So we were able to confirm that these are indeed A stars, similar to what we expect in high mass star forming region, that start dissipating the gas. And again, what is this useful? Why we can use this? Basically because we can use this technique or on these confirmations to add more sources and refine the galactic parameters without having to spend 5,000 hours in the BLBA. That's the region. And this is a study that I start in which you start looking for sources around a maser emission. So in the left one, you are seeing the blue one is showing you, the light blue is showing you where a maser emission is. And in the other colors, what you're seeing is the likelihood to become part of a cluster, or some clusters that are moving close by and therefore could be part of that stellar association. So in the left, you have proper motions movement. In the center, you have an idea of an Hertzsprung-Russell diagram, but actually it is not. It's a color, it's a absolute magnitude, absolute versus color, that will give you an idea of how evolved are these stars. And in the right, you are seeing just basically the sky and a sky map. Again, it's showing you the maser emission with respect to some close by stellar association. And we are trying again to find some isochrones and to feed those because and here is the important part. At the end, what we want to do is add more sources, but we cannot do that with radio observatories, basically because the BLBI time is really expensive. And just to remind you, Bessel used 5,000 hours of the BLBA only to observe 400 of them. And we need to observe thousands of them. We need to go for tens of thousands actually in order to refine our our parameters. And we cannot do this with radio, but we can do a synergy with Gaia and start finding more stellar associations. This again is an example of how we can do it for this particular source and how we can cross some of the techniques. Now let's move to the other project, which is the BAADE project. Again, this is also masers, but now masers with coming from evolved stars, mainly AGB star, Myra type stars. BAADE, it stands for Bulge Asymmetries and Dynamical Evolution Survey. It is led by Laurent Schaberman at NRAO and Ylva Filstrom at the UNM. And they are doing a really large SIO maser survey. They have pre-select on more or less 30,000 targets, 28,000 targets by infrared colors. And they are tracking these sources with the BL8 at Q-band, 43 gigahertz, and with ALMA band 3, which is 86 gigahertz. They are looking for SIO maser transitions at that frequency, and then with that calculate basically line of sight velocities, flux densities, line ratios. But in this case, different from Bessel, they are not doing a follow-up, for parallax, which we are planning to do. We are testing some until what level the astrometry is needed at these high frequencies in order to do that. And we already have done some calculations to find that our estimate of accuracy can go up to 50 microarc seconds in the best case scenario. So again, lower frequency can do this much better, as Bessel already tested. But what is the current status of this project? This project have, again, 28,000 sources, more or less. They point to the whole galactic plane, looking for sources in the bulge. 19,000 of those sources fall for the BLA regime. As you can see in the plot in down, green are the BLA range, black are the ALMA range. And I am glad to say that the whole BLA range has been covered. There has been observed, there has been analyzed, and we already are completed the last publication, which should come in the next following months about this research. And with ALMA, we are having more or less 3,700, and we are hoping to get more. Those are the red points that we are adding there. As I mentioned before, BLBI studies still are in current pilots, and we are trying to use for calibrators at the Q-band in order to create a astrometric strategy that can help us finding parallax for these sources. This is still work ongoing. But again, this is BAADE, and here's the question: what we can add from other frequencies, from other wavelengths? So I start doing this research in which I start cross-matching several surveys, BLA ALMA data coming from BAADE, MSX, TrueMass, WISE, that's infrared, and again, Gaia. And one thing that we have found, and this is the plot of Gaia with some points in green, and I can zoom in those points, is that those BAADE targets that we are detect in infrared and in radio, they seem to correlate pretty well with high extinction regions in Gaia observations. So Gaia is not able to obtain anything from these regions. Of course, it's pretty obscure at optical wavelengths, but this is the first step in which we say, okay, we can contribute to this, and radio and infrared can add a lot over these parts in which, particularly radio, in which Gaia cannot reach. But this is the not matches. Let's talk about the matches. How much of the sources detected by BAADE or planned to be detected, and some of them already been detected by BLA and ALMA, have been detected in a Gaia, in 2MASS and WISE. And something pretty nice is that when we did the cross match, we have found a complete sample of 15,000 stars to study the stellar population at all of these wavelengths. And again, I want to recap here or highlight here that this is all based on astrometry. So that is why we need really good astrometry at all wavelengths, because we can start doing this kind of multi-wavelength research. So BLA is providing us all the information about the SIO emission, radial velocities, flux density, line rates, all the infrareds is giving us all the photometry infrared, and Gaia, of course, is providing us astrometry, parallaxes, proper motions, even periods they have. So with that, we can start characterizing the bulb stellar populations in the galactic plane. And this is a study, again, I want to recap, but they have 28,000, 15,000 of them are in other surveys, so we were able to cross-match. And only for 2,000, and we will see later why is that important, only for 2,000, we were able to estimate a good distance, I mean, extract a good distance from Gaia. So let's leave it like that. I will come back to this. But with those 2,000, we were able actually to characterize the stellar population of this source, characterize this population. So, for example, the evolutionary stage, we were able to find, and here is again an MK absolute magnitude in the K band in the y-axis against colors in Gaia. So you can see that we are crossing two different surveys. And what we have found is that actually our sources, which is the top right part, live in where we expect to be AGBs or red giant stars. Sorry, no, AGB stars or already evolved stars. And other sources in the middle, there were just false positives that we were able to find that there were YSOs. This is a publication also that came out past year. And again, in Lewis et al., which is calling YSOs, she was able, a student at UNM was able to find that some of those sources are indeed YSOs, but most of them, we are happy to say that they are AGBs. So we have a really good 2,000 sources of AGBs. Also, something that you can obtain when you have all of this information, including extinction maps, and I should say that, we also have extinction maps at this level, so we can find pretty well what is the volumetric magnitudes of these stars. So in the red and blue, you are seeing two different samples of other study, assuming other distances. But the one that I want you to highlight is the black one, because it's the one that we were able to calculate. And we have found that these stars have a luminosity of around 1,500 solar luminosities. And this is an important thing, because when we refer to AGBs, we are expecting much brighter sources. Oh, something happened. Sorry, can someone hear me?
Hi, we can hear you, Luis.
You can see my presentation?
No, it's a white screen.
I will stop sharing and share again. I'm not sure what happened. Let me end this. Sorry about that. I'm not sure what was happening. Okay, can you see now?
Yep, and full screen, you're good.
Okay, sorry about that. So the idea that I wanted to give you with this is that we were finding that these stars actually have much lower luminosity than we were expecting. And we are now to find what implication has of this, of, for example, period luminosity relations. Do they behave similar to what we see in the LMC or the SMC or in the bulge? So obviously the metallicity is different, but at least we are finding that the luminosity distribution is not the same. And I want also to leave you with this image, and we were able to put it in a top view of the Milky Way. we are pointing to the sun. The center here is the sun. And you can see some of the large scale structures like the local arm or the recently discovered Radcliffe wave where it's passing. And here are the AGBs around. So with this, what we are doing is trying to show you that they do not correlate with large scale structure. They are indeed dynamically relaxed, as we expect from the above the stars. But again, we are extracting much more information. This was just the first publication in a series of at least 2 more. And the other 2 that are kinematic studies are coming. But I want to go back with what happened with the 13,000 sources that we missed. Again, we have 15,000 cross match with parallax available, and we end up with only 2,000 of good distance. And what we mean with good distance, basically the idea that we have in our minds for the parallax and distance relation. So if you have a distance, you inverted it and you have a parallax. Sorry, if you have a parallax, you inverted it and you have a distance. And you can express the error in that distance as the equation is showing you up there. However, and it was this is a problem that has been widely studied, you can only do that as long as your errors in the parallax are less than 20%, the relative errors. And this is what is happening not only to our study, but to most of the Gaia data. And I should again say that, and is for our study, 19,000 of our sources has more than 20% error in the parallax, and 14,000 of that have negative parallaxes. And here's the question, what it means a negative parallax? How we can use the negative parallaxes in order to study stars, because we have no idea of the distance, which is a basic parameter to establish physical properties. And again, that's a great question, how we can do that. So, but here is again, when I'm trying to say, there are the synergies that we can use to constrain this. What we have, let's do a list of what we have. We are sure about the population that we are studying. Here at the BAADE, we say, Gaia has classified this star as Myra. They have SIO maser emission. In infrared color selections that we made are indeed evolved stars. We have periods coming from CTF or Gaia or AABSO or for the BBB survey in the south. And even the Hertzsprung-Russell diagram in evolutionary stage is confirming that they are indeed AGB stars. So we have a very well-defined population. That's something that we have. What else we have? We know some absolute properties of these populations. For example, as I showed before, for this population, we were able to calculate volumetric luminosities, but we can also calculate absolute magnitudes in a particular band, pass band, in this case, the K band in infrared. So we know this property very well, and we also have relative individual measurements of that general property. For this, again, 13,000 with negative parallaxes, bad parallax, whatever, we still have information about each one about 2 mass. So it's coming, the apparent magnitude is coming, and we know what should be more or less the absolute magnitude expect. And this is important because with this, you can create a prior or constrain, I want to say, your distance in order to move from a negative parallax that is giving you no information about the distance to something real, to something that you can actually do. And again, we start doing this research, we start building up a prior using infrared data, using optical data, but using confirmation of SIO maser. That is why in radio, that is why it's a synergy between all to create a posterior distribution. And we call this the photometric distance probability density function. So it's too complicated, so we put it PhD PDF because it is another level. So we start testing this with real sources. Here is a source from BAADE that Gaia is saying that has a parallax of 1.295. So it's only a 50% parallax, so you can safely invert the parallax to obtain a distance. And the distance, which is the yellow, the green line, vertical line, is telling you that that distance is around 772 parsecs. Now, with the whole project that we have built up, and I don't want you to go into the details of that, but we can go if you want. we construct a posterior distribution that in this case is telling us that is 764, and the plus minus you can see that are slightly shift. But we have shown that it works pretty well already, not only with Gaia data, with good Gaia data, so parallax less than 20%, but actually we have generated mock data from simulations and from the Bessel survey actually, and it works pretty well. Now, the question is, okay, you are able to do this, and here is more or less what you will obtain. Again, we are showing in the y-axis is our distance estimate using this PhD PDF, and in the down is just inverting the parallax. And again, this is for a sample of very, very good parallax measurements. So we can show that for our BAADE survey, for the 2000 surveys, we can use easily both. But here is what comes the advantage, and is we can use our posterior to actually find distance over negative parallaxes. And here is or high relative error parallaxes. And here is an example. This is another source that is pointing to the galactic center, and Gaia is saying this has minus 0.017 milliards seconds, which means nothing, because we cannot invert that, otherwise it has no sense. But again, the posterior, because we know exactly what are the type of stars that we're observing, we know what is the absolute magnitude that we expect from these sources, and we have apparent magnitudes of these sources. We can use those constraints in order to fit much better, in order to create a posterior distribution. And for these sources, our posterior distribution is telling us that this is around 1.4 and almost 5 kiloparsecs, which is huge. But here's what I want to highlight again once more, and it is huge if you want to study this particular source. That's right. But if you want to use this over thousands of sources, that's what we have in BAADE, or even billions, that is what Gaia is providing, this is very useful in statistical studies. And just to remind you, this source was pointing to the galactic center. So one of the conclusions of this, for example, was that this is not a bulge star, because we expect that the bulge star from 5.5 or even more, the bar stars or more, given the situation, given this calculation, we can be sure that this is likely a disk star, and we can start distinguish which stars are by sure part of the disk or by sure part of the bulge, and study independently, even if we don't have the precise or the accurate, distance to those stars. I also want to highlight that in these particular methods, we are not using the normal sigma that we expect in the errors. So the distance here are 90% confidence intervals, basically, different to what you expect in a Gaussian distribution with the sigma. I think that this is the end of my presentation. For future in the Bessel, the young massive star, we are keep looking for optical companions to confirm some stellar associations. And now I know that Bessel is moving to the south and is trying to get from some arrays in Australia some of the sources in the south. But again, Gaia can complement this, and this is what I'm trying to tell you here. And for the bulb stars, we already started studying the kinematic study, and for example, what is the luminosity distribution of the SIO masers, which we can also use in the posteriori distribution to refine our distance estimates. And we already got some maser emission detection in the BLBA in order to refine pretty well the astrometry that we can reach at Q-band. And we are trying to show that these radio campaigns are actually not competing with Gaia, not competing with infrared, but are actually supporting techniques in order to give us a better understanding of the populations in the Milky Way. And if you lose completely your mind during my talk, but you like this show, I want to highlight that in their offices, sometimes they like to put my plots, and I'm really proud of it. So probably if you see this show again, you will remember my talk and come with some questions. That's all that I have to say.
Wow. Well, thank you very much, Luis. And that's a very exciting cameo by your lovely work. Wish you had gotten compensated. But All right, so open the floor. Does anybody have a question they'd like to ask about his work? Feel free to unmute yourself.
Yeah, this is Jay Lockman.
Go ahead, Jay.
Okay. Could you talk a little bit about what you've learned about the rotation curve in the outermost parts of the Milky Way from these studies?
Sure. So about the rotation curve, here can you see my screen? Yes. Here in the down part, you can see the rotation curve published by this one. Sorry, this one is wrong. This is the 2014 plot. Uh, what we have learned so far is that masers actually are providing, again, pretty well values in terms of the component of the tangential component of the galaxy. And so far, with the level that we can reach, it seems to be pretty flat. The value, as you can see it in the third row on that table, is our estimate was minus 0.2 kilometers per second per kiloparsec, the estimate. But here is the important thing, and is we are relying basically on the outer arm observations because those are our best shot in order to provide that long, the longest radius estimate. We are hoping that we can get more in that direction, but and particularly with Gaia and this particular source S269, we are hoping just to add more points to that rotation curve. But so far we haven't published that. We are still trying to confirm first that the Gaia counterparts are indeed part of the stellar association. We have done that for S269, but we have a couple of sources in the outer arm, and we are testing if we can do the same for others in order to add more. These are basically our results in the rotation curve.
Now, let me just follow up in the sense that there is another group that has an acronym, and I can't remember what it is. It's like the Galaxy Project or something like this, which is deriving the motion of the sun to quite high accuracy from a number of different tracers, and they get maybe 2 sigma smaller R naught than you do. Or put it differently, is there any tension between these numbers that you derive and numbers derived by other groups using other methods?
There are always tension. I think that I don't have the plot here of how, for example, the distance to the center of the galaxy have been moving over the years. But what I can tell you is that I know about gravity, for example. Gravity even surpassed the level of the distance to the center of the galaxy, and there are some things that are in disagreement. But it is not dramatically bad. I mean, it is not something that will cause a real impact in extragalactic measurements or the measurement of the Hubble constant or something that goes farther than that. But indeed, these tensions, we continue publishing, we continue refining, and we continue collaborating. Each time that we are able to see something in the literature that claims something different, we try to compare and we try to add it and see the implications of that. Because at the end, what we are looking for is to provide to the community good or accurate values of the fundamental galactic parameters of the Milky Way. Again, the answer is I don't expect that there is a big tension, but differences in the values, yes, they are, with not so much implications. I will take the word to say that.
Right. Okay. It was the gravity collaboration. Thank you.
Yes. Okay.
Yeah. Thank you.
All right, thanks, Jay. Does anyone else have a question? And if in the meantime, I was just curious, Luis, have you introduced any of the Gaia Data Release 3 preliminary results into your work?
Yes. Can you hear me? Yes, sure. So Gaia DR2 has provided much more data. I was involved with the people that delivered that, and basically because I'm studying MIRAS, in the Gaia DR2, they were able to provide periods for not all of them, but a good sample of my sources. So I was really interested in that, and I follow up mostly the Gaia DR2 IM base. Now the Gaia DR3 is providing better accuracy in terms of astrometry that we have already tested and is not affecting our results so far. But that's again the early Gaia DR3. The DR3 is coming, and here is going to become interesting because they are coming, for example, with radial velocities, and we will see how they correlate with radial velocities in radial regimes coming from the spectral lines, which is what we do in masers. So it is going to be exciting in the next couple of years. It's good to be alive in the Gaia era, I would say. Sorry.
Excellent. All right, we have time for maybe one more question, if anyone would like to ask Luis.
I can ask a question. So there has been evidence for a warp in the galaxy. So with the data that you have, can you see some evidence of that? And maybe it's just my ignorance.
No, it's not.
Okay.
It's not a bad question. Yes, there has been evidence of warp, and we can say that in the warp is coming like in this. I don't know. Can you see my plot? Yes. So in this figure, for example, you can see up the yellow star. That's the sun. Basically, this is projecting in the galactic plane, but in that part, in the yellow part, is slightly up and then seems to be down. That's more or less the warp how it's going. We have seen evidence of the warp, yes, but again, we are talking about 400 sources here, so it's 400 points in a grid that you have to reconstruct completely the warp. So I would say that if you keep doing radio observations, following up with parallax, and you will spend 5,000 hours to get 400 of them, it's going to be complicated to fill up that grid in order to recreate properly. But probably with Gaia, finding the stellar associations to these arms, it will be much easier. The thing is that again, Gaia is producing the sources, and but we have to confirm that are indeed embedded in these arms, and that is why the high mass forming regions, the proof of masers, is our best tool. So again, as only if we base only in the radio observations, we can say that there are some evidence of the warp, but we cannot confirm it or model it with the data that we have right now. That will be my answer.
Great, thanks.
All right. Well, we're just about at time, so I want to thank you again for joining us and giving us a little bit more information about your work. So with that, I'd like to wish you all a good rest of your week, and to let you know, next week we will be having a talk by Sangeeta Malhotra. But otherwise, take care, everyone. Again, thank you very much, Luis. It was great talking with you.